Pull out your phone right now and open Maps. In a few seconds, a blue dot appears, pinpointing you on the planet with terrifying accuracy. Your phone can tell you're standing in your kitchen and not your living room. But here's the thing. No one is watching you. No camera, no tower nearby scanning your face. Just a handful of satellites in space, silently triangulating your exact position. How on earth does that work? Let's break it down. GPS, the Global Positioning System, is one of those technologies so embedded in daily life that we forget how remarkable it is. From delivery drivers to aircraft pilots to hikers lost in the wilderness, GPS has become the invisible backbone of modern navigation. But the science behind it is genuinely mind-bending. It involves orbital mechanics, the speed of light, and a touch of Einstein's theory of relativity. Buckle up. The GPS network consists of at least 24 operational satellites orbiting Earth at an altitude of about 20,200 kilometers, roughly halfway to the Moon. These satellites orbit the Earth twice every day and are arranged so that from virtually any point on Earth, you can always see at least 4 satellites in the sky, even when you can't physically see them. The U.S. Department of Defense originally built GPS for military use in the 1970s and 1980s. In 1983, after a Korean Air civilian flight was shot down after accidentally entering Soviet airspace, partly due to navigation errors, President Reagan made GPS signals available for civilian use, and the rest is history. Today, other countries have their own systems. Russia has GLONASS, the European Union has Galileo, and China has Beidou. Your modern smartphone likely uses all of them simultaneously. Here's the core of how GPS works, and it's a concept called trilateration. Each GPS satellite constantly broadcasts a radio signal along with 2 key pieces of data, its exact location in space, and the precise time the signal was sent. Your GPS receiver, your phone, picks up these signals and calculates how long each one took to arrive. Since radio signals travel at the speed of light, about 300,000 kilometers per second, even tiny differences in arrival time correspond to real differences in distance. Picture each satellite drawing a giant sphere around itself. The device is somewhere on this sphere. With one satellite, you could be anywhere on that sphere. With 2 satellites, you narrow it to a circle where the 2 spheres intersect. With 3 satellites, you get 2 possible points. With a 4th satellite, you can pinpoint the exact location in 3-dimensional space, latitude, longitude, and altitude. This is why your GPS needs to acquire at least 4 satellites before it gives you a reliable fix. The more satellites your receiver can see, the more accurate your position becomes. Here's where it gets seriously mind-bending. The whole system depends on insanely precise timing. We're talking nanosecond accuracy, billionths of a second. Each GPS satellite carries atomic clocks accurate to about 1 nanosecond. At the speed of light, a 1 nanosecond error would translate to a 30-centimeter position error. That's significant. But here's the wild part. Einstein's theories of relativity actually affect GPS satellites. The satellites are moving fast, about 14,000 kilometers per hour, and are high above Earth's gravity well. According to special relativity, their clocks tick slightly slower due to their speed. According to general relativity, their clocks tick slightly faster because they're in a weaker gravitational field. The combined effect? Without correction, GPS clocks would drift by about 38 microseconds per day, making your GPS position off by about 10 kilometers every day. So engineers build these relativistic corrections directly into the GPS software. Your iPhone is literally running calculations derived from Einstein's 1905 theories every time it shows you where to turn. GPS isn't perfect. Several things can mess it up. Buildings, mountains, and dense tree cover can block or reflect satellite signals. This is called multipath error and is why GPS is less accurate in urban canyons. Atmospheric interference, particularly in the ionosphere, can slow down signals slightly. Solar storms and geomagnetic events can degrade the signal across large areas, and in some countries, governments intentionally interfere with GPS signals, a practice called jamming for military or political reasons. Near GPS jammers, your location can jump wildly or disappear entirely. GPS enables more than navigation. Precision agriculture uses GPS to guide autonomous tractors within centimeters. Financial systems use GPS timestamps to synchronize global transactions. Emergency services use it to dispatch responders. Scientists use it to measure the drift of tectonic plates. GPS is accurate enough to detect the Earth's continents moving a few centimeters per year. The future of GPS will be even more precise. Next-gen systems promise centimeter-level accuracy for consumer devices. Autonomous vehicles require this level of precision. GPS alone isn't enough, which is why self-driving cars combine it with LiDAR, cameras, and AI to create a complete picture of their surroundings. We're also moving toward quantum positioning systems that don't rely on satellites at all, using quantum physics to navigate in environments where GPS can't reach, like underwater or inside buildings. So, the next time your Maps app casually tells you to turn left in 200 meters, appreciate the ballet happening above your head. 24 satellites, Einstein's equations, atomic clocks, and the speed of light, all working together to put a little blue dot exactly where you're standing. Technology is extraordinary when you actually look at it. If you found this fascinating, smash that like button and I'll see you in the next one, where we tackle something even more counterintuitive, how hundreds of tons of metal actually fly.